Okay, so today I'm going to be recording the solution to the third practice problem for homework number 5. Okay, so what that looks like is we have a plane wall of length for 1/2 L, and then this is at some initial temperature. And so what happens is, at a sudden moment in time, we apply convective cooling to both sides of the wall, and also heat generation begins to occur within the wall. Okay, and what the problem wants us to do is to find the finite difference equation. This would be for transient, because this is a transient problem, right? We started at an initial temperature, and now we're cooling the wall. We want to find the finite difference equation for a surface node. Okay, so our energy balance / control volume step, I'm actually going to skip for now because we're going to do that as part of the analysis. But I will write down our approach, which is to use the energy balance method. This is the method I've taught in class about how to derive how to derive finite difference equations for nodes within solids. Okay, so let's actually do that. So for our analysis portion, I'm going to draw the surface right here. On one side, we have T infinity, and then I'm going to draw this node right there. So that is the node that is on the surface, and I'll label that as node 0. And then I'm also going to label another node as node number 1. So you remember we have 5 steps when we do the energy balance method, where the first step is to draw the node of interest and any nodes around it. So we've actually just done that first step. Okay, the second step is to draw a control volume. So that control volume, we go halfway between node 0 and node 1 and draw a surface. And now, in the solution, this is treated as a 1D problem because it is. So this normally actually extends upwards forever, up and down. However, what I'm going to do is I'm going to actually give it a finite height. I just find it's a little easier to understand the problem. I'm also going to incorporate the rightmost boundary into our control volume and go just barely past it. So that is our control volume. Our third step is to draw the heat transfer terms. Okay, so coming in from the left, we have conduction from node 1. We'll call that QA. And then coming in from the right, we have convection from T infinity. So I'm going to just label that as QB. Alrighty, so we've drawn our heat transfer terms. So now we have our next step, which is sometimes the hardest, and that is to write out our heat transfer terms. And we're going to do this in terms of the temperatures of surrounding nodes. Okay, so QA prime, that's our conduction from this left node, node 1, to node 0. Since it's conduction, we start with the numerical approximation to Fourier's law, or K, and then we're going to multiply it by the area. So the area will be equal to this vertical distance times some unit depth in and out of the board. So that control volume has a height delta y. I should actually label these. So the distance between nodes horizontally is delta x. And since our control volume only extends half that distance, then the control volume bottom boundary is actually of delta x divided by 2. Okay, so we have k times delta y, and then we're going to multiply by the temperature of the node it came from, so T1, subtracted from the temperature where it ended up, or the temperature of our node, T0, divided by the distance that was conducted over, or delta x. Okay, next we are going to do QB prime, which is convection. Okay, so for convection, we have H times the area, which is again going to be delta Y, multiplied by the temperature where the heat started, so T infinity, subtracted from where it ended up, or T0. Okay, so we have those two terms. And let's not forget, I should have labeled this, we have heat generation. That's, of course, going to come in step number 5, which we are now ready to do, which is the namesake of this method. We're going to do an energy balance on the control volume. So any energy balance on a control volume, you'll remember, is the energy going in minus the energy going out plus the rate of energy generation, which is equal to the change in the stored energy of the system. Okay, so we actually have no heat leaving. That's because we always define our heat transfers going into the control volume. So we can plug QA and QB here into our E in term, and then fill in terms for E gen and delta E stored. So first we plug in terms for our E in. So I'm just going to take these two up here and move them down here. Okay, now we need to add E gen, which would be the heat generated times the volume of our control volume. So we stick with Q dot, but then we need to account for the volume. So our control volume is delta Y tall, and then it's delta X divided by 2 wide. And finally, we need to set that equal to something. So this delta E stored term, normally we write as rho times V, or mass, times the specific heat, times the change in temperature with respect to time of our node of interest. As we discussed in class, the way this will come out is density times our volume, or delta X divided by 2 delta Y, times our specific heat. I'm running out of space, so I'll do this down here. Now we need to approximate our time derivative for temperature. And the way we're going to do that is we're going to write it as the temperature of our node 0, at a moment in time, P plus 1, subtracted from that same node, but now at the current moment in time, P. So this is the temperature at this moment in time. This is the temperature at the next moment in time, divided by the difference between P and P plus 1, or delta T. So how much time elapsed between P and P plus 1. Okay, so you can see we now have a full expression giving temperatures of node T0 and T1 as a function of each other. And that's what we are trying to get. However, we have this issue. We need to identify for these terms right here, these temperature terms, are they P or P plus 1? And so we're going to explore that right here. There are two approaches. There's the explicit method and the implicit method. I went over these in class, but briefly, an explicit method is we assign each T that is currently unlabeled as having P. Okay, so when we do this, we're going to go up a little bit so we can see both things. Okay, now we'll remember that delta Y equals delta X. And if we allow that, we can actually simplify our expression a little bit. So we're going to apply P to every single one of these equations. So we have K, and we're going to cancel out these terms. So K times T1P minus T0P. Again, this is explicit, so we're assigning P. Plus H times delta Y times T infinity, which is a constant, so we don't have to give it a P value because it's not changing with time. Minus T naught, which does have a P, plus Q dot, which again is a constant, so it doesn't need a P or anything. And we can combine this delta Y and delta X into one term. And that will be equal to rho delta X squared over 2. So I combine the delta X and delta Y times specific heat times what we already had, t naught p plus 1 minus t naught p divided by delta t. Okay, there we go. So that's the explicit method. Now, what we're going to do is we're going to rearrange this to get everything as a function of just t naught p plus 1. I'm not going to go over that algebra for you. I would encourage you, obviously, to do that yourselves. But rearranging that, we get the following. Again, I'm not doing this math for you. I'm just giving you what happens after we did the algebra. Okay. Takes a while to write this out, sorry. Okay, so there's our final expression giving t naught p as a function of these other temperatures, these other nodes that are at the moment p. So we have t naught p plus 1 as a function of any temperature at p. Okay, we can actually simplify this more. Specifically, let's break this out right here. So we have, and I'm going to kind of do some interesting things here. So we have an h, which we'll put over here, and we're going to divide that by a delta x. Okay, and we're going to move these other terms over here, delta t over rho times c. So now I'm going to do this really weird, interesting thing. I'm sorry, I actually wanted this delta x to be over here. So I'm now going to multiply this by delta x over delta x and by k over k. I'm allowed to do that. We're multiplying by 1, right? This is 1, this is 1. And when we do that, we get h times delta x over k. So h times delta x over k multiplied by, we had a delta t on the top, delta t, and we have a k still on the top, divided by rho times c, and now we have 2 delta x's, so delta x squared. Okay, one more thing. So h delta x over k, that looks a lot like the BO number, h times the characteristic length over k. In fact, this is the BO number, so we're going to just write BO number. And then this right here, we're going to rewrite as delta t. And now we have a k over rho times c. That is the same as alpha thermal diffusivity divided by delta x squared. Well, you would be right if you said that looks familiar, because that is the Fourier number for a finite difference equation. So we end up with BO times Fourier. This whole term right here becomes BO times Fourier. You can do the same thing to this expression, and you end up with just the Fourier number, because you see we have a k over rho c, that's alpha, so alpha delta t over delta x squared. You say, well, wait, we multiplied every term in this equation by delta x over delta x times k over k. Don't need to do that here. But again, we just multiplied by 1 in this case, and we didn't allow those to go any further. Okay, but then we need to look at our q dot case right here. Here we're going to do the same thing, where we're going to multiply by these terms, and when we combine those, then we're going to be left with some new terms, out of which we'll get the Fourier number and still be left with a delta x squared and a k. Okay, so taking all this into account, your final expression is t naught p plus 1 equals 2 times the Fourier number times t1p plus the BO number times t infinity plus q dot x squared over 2k plus 1 minus 2 times the Fourier number minus 2 times the Fourier number BO number times t naught p. Okay, so that's the final answer using the explicit method. Okay, we can also do this again using the implicit method. So remember, the implicit method is when we label all temperatures now as P plus 1. So going all the way back to the top, right here, this expression, we're going to label these T terms now as P plus 1. So you see we're going to have a lot of P plus 1s and one P term. So when we write that out, then we get this expression, H times T infinity minus T naught P plus 1 plus K times T at node 1 P plus 1 minus T at node 2 P plus 1 divided by delta X plus Q dot over delta X over 2 is equal to rho times C times delta X over 2 times P naught, T naught P plus 1 minus T naught P divided by delta T. You'll notice I've divided by delta Y here just to simplify our expression. Okay, this can be rearranged, and we're going to use the same trick we did up here. Let's see, where we multiplied by 1 in a funny way, or K over K and delta X over delta X. And we're going to use that to turn some of these terms into BO numbers and Fourier numbers. And so after we do that, then our final expression looks like this. 1 plus 2 Fourier times BO plus 1, these are square brackets, times T naught P plus 1 minus 2 times the Fourier number times T1 P plus 1 is equal to T naught P plus 2 times the BO number times the Fourier number times T infinity plus the Fourier number times Q dot delta X squared over K. Okay, now you see that we've lumped together all of our P plus 1 terms as a function of just our single P term. And this we would solve by generating a matrix equation, our A matrix, which is our coefficients, or these parts of our temperatures. And then we'd have this vector, which would be all of our P plus 1 temperature terms. And that would be equal to our source terms, or this entire side of the equation, which I won't write out. You would invert this matrix, multiply it on that side, and right there, and be left with just this vector, which you've then solved for. Okay, thanks for watching.